Great. So yeah, so as I was saying, the talk of my thesis, the talk title and also my thesis title is Complexity, Algorithms, and Applications of Programmable Quantum Many-Body System. And I want to sort of ease everyone in a bit since this is really early in the morning, especially for those of us joining from California, by first establishing some common language and provide some motivating background for my work. So many of you already know this, but I think that everyone likes to hear things they already know. So the reason why we're interested in quantum many-body systems is that they are incredibly complex. Well, how complex? Well, in contrast, consider a normal classical systems, for example, say like n billiard balls. The state of this classical system can roughly be described by n variables. For example, the positions and velocity of the n balls. But more abstractly, you can think of it as a classical system can be described by roughly n bits, which can either be zeros or ones. Now, what about a quantum system? If you have n quantum particles, the correct description of the state of the system is something called a wave function, psi. And a wave function, as in analogy to an actual wave, can have positive and negative amplitude. In general, this wave function can be described by vectors of these positive and negative real numbers, or even imaginary numbers, in the sense that each entry in this high dimensional vector correspond to the amplitude of observing the classical, the degrees of freedom in a particular state. For example, if you have n bits, there are in fact 2 to the n different possible configurations. So the complexity of a quantum system really is given by a wave function that's described by 2 to the n numbers, not just n. So as you can see that, this kind of quantum systems, especially when you have many particles, is incredibly complex compared to a classical one. And when we want to study nature, and one of the key things that we want to do often is to simulate them. And because of the complexity of these quantum systems, it has been sort of, people have had trouble actually being able to simulate them on our normal everyday classical computer. And this is really one of the main motivation for why we want to study how we can actually manipulate and program quantum many-body systems to suit our purpose. And as this is identified as a key insight by Richard Feynman as early as in the 1980s, actually, I think essentially exactly 40 years ago, that because nature isn't classical, and if you want to simulate it, it's much easier to do so with a quantum mechanical computer than a classical one. So you may ask, okay, sure, quantum systems are complex and they're hard to simulate, but are they actually useful? Do we ever need to simulate them? And this brings us to my next point, which is that indeed, these quantum many-body systems, if you can program them, they can be incredibly useful. And this is shown by pioneering work by Peter Shor in 1994, that he discovered that if you have a quantum system that you can program in like a quantum computer, you can actually use it to factor really large integers. And this integer factoring problem has a lot of real world applications, especially in cryptography. And just to sort of drive the point home, if you consider the runtime of factoring n-digit integers, the best classical algorithm that we know of has a runtime that scales roughly exponentially in the number of digits. But using Shor's algorithm, you only need to do it on a quantum computer with only time that's n squared, a polynomial. And sort of this exponential to polynomial speed up is really what motivated a lot of us today to try to study quantum computers and quantum many-body systems. So while this sort of Shor's discovery is sort of very inspiring, and one may even start to think, okay, this computer seems to be more powerful than the normal everyday computers, but can they solve all the problems in the world that we have? Well, this question about how powerful quantum computers are is actually very complicated, and And we do believe that, there is limit to the power of quantum computers, and this is addressed by complexity theory in computer science. So I will paint you a picture. In complexity theory, they define sort of the families of problems that you can solve on a classical computer as the complexity class P, which stands for polynomial time. For example, the problem of finding a shortest path on a graph or between two cities, for example, when you're given a map, is considered a problem that you can indeed efficiently solve on a classical computer, and that's therefore in the complexity class P. Now, if you have a quantum computer, then the number of problems you can solve is believed to be bigger, and indeed, factoring integers as shown by Schur is believed not to be in P, but but it is in something called BQP, which stands for bounded error quantum polynomial time, and that's basically the class of problems that quantum computers can solve. But then, we don't really expect quantum computers to solve everything because there's a family of problems called MP, which we believe that contains problem that's even harder for quantum computers. And for example, if you consider optimization problems, it is believed that potentially in the worst case, these optimization problems which are in MP, and they're actually complete for the MP class, which means that any problem in MP can be mapped or reduced to a problem like optimization. And it's believed that in the worst case, these optimization problems are probably even too hard for quantum computers. But that does not rule out that perhaps in some special situations, or maybe on average, quantum computers can provide a computational advantage. But in addition to optimization problems, there's also the problem of simulating quantum systems or simulating the dynamics of quantum systems. And it is believed that these sort of problems are not really within the realm of the capabilities of classical computers. So it's believed not to be either in P or MP, but it is within the realm of the capabilities of a quantum computer. But we also know that there's definitely problems that even a quantum computer cannot solve. And this is sort of captured by the quantum generalization of MP. And this is something called the QMA class. And just as a fun fact, it means quantum Merlin-Arthur. And this is the kind of the class of problems where we don't know how to solve them with the quantum computers, but we can check if the answer is correct with the quantum computer. And for example, the problem of finding the ground states of general quantum antibody systems is considered to be, it is complete for the class of QMA, and it's believed you cannot even solve them even if you have a quantum computer. So what can we do now with the capabilities we have for today or soon? Well, the bad news is that we don't really have a quantum computer right now. Well, we're working on it, but the good news is that we have made a lot of progress, and the current technology we believe has really broken through the barrier of the capabilities of classical computers, and we have started to explore possibilities of doing something really non-trivial with optimization problems as well as simulation of quantum systems. And I will give you a few concrete examples of the capabilities of current technology. And I would describe that these new capabilities has ushered in a new era of programmable quantum systems. And one of the exciting capabilities that have developed recently is some really cool experiments that have exhibited incredibly fine levels of quantum control. For example, in some work done by Manuel Andres and others in our group, they were able to rearrange and assemble atoms in arbitrary configurations using optical tweezers, almost like a Maxwell demon. And they have already applied this technology to perform analog simulations of quantum models, to perform really interesting quantum phase transitions in systems as large as 250 atoms, which you cannot really simulate at all on a classical computer. And also they're trying they have been able to study exotic physical phenomena like quantum spin liquids. And this is recent work done by led by Seffer and Julia just in this past year. In addition to atoms, there are also other platforms that have made a lot of progress, like superconducting qubits. And some of you may have heard about this, that Google was able to claim that they have demonstrated quantum supremacy using superconducting qubits, roughly 50 of them, into 2019. And some of these experiments have also started testing real-world applications such as optimization on these devices. And in fact, I was actually fortunately enough to be involved in Google's effort to use their quantum processor for optimization. So motivated by these exciting developments of programmable quantum many-body systems, I have made a number of contributions in understanding the complexity of these systems, as well as developing real applicable algorithms and scientific applications from them. So they're roughly divided into three categories. So the first one, the first contribution I have made is in the realm of analog quantum simulation. And this is based on work that I've done with Doria Harana from Hebrew University. And there we were able to show some rigorous resource lower bounds for simulating Hamiltonians, which describe quantum many-body systems. And we were able to also provide exponentially more efficient constructions for doing so. Now, for the problem of quantum optimization, in a joint work done with Chantal Wang, Seung-Won Choi, Hannes Pickler, and Misha, we were able to study a very general purpose quantum optimization algorithm called the QAOA, and identify very important parameter patterns, as well as a working principle for the algorithm that shed light into how one may actually use the algorithm for a potential quantum speedup. In addition, working with Eddie Farhi and Jeffrey Goldstone and Sam Gottman, we were able to actually derive rigorous analytical results on the typical performance of the QAOA. And we believe that our techniques have provided a way forwards towards a provable quantum speedup in quantum optimization. And in addition to this more abstract ideas of simulation and optimization algorithms, I've also made a number of contributions in actually coming up with ways to engineer quantum systems and harness their many-body dynamics, so we can actually do the things that we want to do and potentially perform other scientific applications. For example, with Seung-Won Choi and Misha, we came up with a way to really use dissipation, which is considered a source of noise in the experiment, and harness it actually as a resource to generate many-body quantum entanglement in the system. And the protocol that we came up with actually has a lot of intrinsic robustness that we believe is better than many of the other protocols people are using today. And in another joint work with experimentalists like Sergio Cantu and Aditya and Wen Chao in Vlad Vuletic's group at MIT, we are also able to come up with a way to engineer a repulsive interactions between photons, which can be important because photons are considered ideal carriers of quantum information. And if you can get them to interact in a non-trivial way, you can potentially use them for not only information communication, but also processing, and really linking the different platforms of quantum processors together. So for today's talk, I'm going to focus mostly on the first two topics. And I will start by telling you about my work on analog quantum simulation. So to begin describing my work, I want to actually first take a slight detour into sort of computer science language, because I think that it really provides some context for the problems that we're interested in. And in computer science, a very classical and important concept is the constraint satisfaction problems. or CSPs. So classical CSPs are functions really defined on hypergraphs, which we call their interaction graph. And a hypergraph is essentially a collection of vertices with edges that could involve, not only just 2 vertices, but also 3 or 4. Now, a KCSP is a function consisting of a sum of terms, each corresponding to a constraint on a hyperedge of at most k nodes, k vertices. And each term evaluates to 0 if the constraint is satisfied, or 1 otherwise. So a KCSP really is a function that maps assignment of bits on the nodes of the graph to a non-negative integer corresponding to the number of constraints that are violated by the assignment. So there's a very famous theorem that really started the field of complexity theory called the Cook-Levin theorem that tells us that it is NP complete is a problem to decide whether or not the minimum number of violated constraints is below or above some given thresholds, A and B. So why am I talking about classical CSPs? Well, because they are essentially a natural analog to Hamiltonians, whereas Hamiltonians are essentially quantum generalizations of classical of CSPs. So instead of talking about KCSPs, there's something called a K-local Hamiltonian, and this is similarly defined as the sum of terms over their hyperedges, where now each term is now not just a function on bits, but a generalized Hermitian operator acting on at most k nodes. So I would like to emphasize here that the notion of locality here is a bit different. So k-local here only means that you only have k-body interactions, and it has nothing to do with the spatial locality that's in physicist language. So and I need to describe a couple more parameters. So first of all, so the norm, the spectral norm of each term in this Hamiltonian, which is basically, if you think about this is basically the largest eigenvalue of the operator, we typically consider them to be bounded by some number j, which we call the interaction strengths. So more physically, what this means is simply that these terms describe the interactions between particles, and their magnitude is bounded by some number, which describes the largest interaction in the system. And indeed, these Hamiltonians, which I have been sort of talking in abstract, each of these Hamiltonians describes a potential quantum system. And in physical systems, typically the locality K as well as the interaction strength J are typically bounded by some constants. So they're not really, believed to really to be allowed to increase with the system size, for example. Now, in 1998, Alexei Kitaev has famously quantized the Cook-Levin theorem and showed that the problem of deciding whether a K-local Hamiltonian, whether its lowest eigenvalue is below or above a certain threshold, that problem is complete for the class of QMA. So that problem is considered very hard, even for quantum computers. And this is why I was saying earlier that even the problem of finding the lowest energy state, the ground states of quantum Hamiltonians, can be considered hard for even quantum computers. So now I have defined what Hamiltonians are to you and put it in the context of computer science. I will now describe the topic that we're interested in, which is analog quantum simulation. And this is essentially the task of replacing a given Hamiltonian H by another one H tilde, so that all of the essential properties of H, the original quantum system, is reproduced. And we're interested in this from two angles. One is that this is analogous to the fundamental idea of reductions in classical computer science. So in classical computer science, you map sort of problems to problems. You map, for example, the traveling salesman problem to maybe the problem of finding the largest cut between in a graph, and that's basically the mapping between CSPs. And similarly, the mapping between Hamiltonians is a very fundamental idea in quantum computer science. But more physically, this sort of analog quantum simulation is an important motivation for building quantum computers in the first place, as identified by as early as 1980s by Feynman, and more recently by Sirach Zoller and John Preskill. And the idea here is that if you have a complicated Hamiltonian H that you're interested in, that you cannot easily access in nature, perhaps is if you can map it to a Hamiltonian H tilde that's more easily implementable in the experiment, then you can just implement it and study all the properties that you would need. And this is this concept of analog simulation is in contrast to digital simulation, where we only care about simulating the dynamics under the Hamiltonian H, which is this e to the minus IHD operator by a quantum circuit. So instead of building a quantum circuit to do the simulation, what we do is simply building a analog model in the experiment that hopefully reproduces the properties of the original system for free without doing any sort of a circuit control. So
Leo,
now let's be a bit more. Yeah.
So you assume some kind of trotterization to get from discrete gates an actual continuous Hamiltonian.
Yes, in the context of digital simulation, that is definitely necessary. Digital simulation is really you're only allowed to use some set of universal discrete gates, like you only have a finite number of them, and the idea is to decompose the evolution e to the IHT with trotterization, or maybe more sophisticated methods like quantum signal processing to map it to a collection of single qubit and 2-qubit gates like I have pictured.
And do you impose any constraints on this error of trotterization?
Yes. So in general, because of the fact that one can show that you only for any target precision epsilon, this kind of digital simulation is you can do it with only sort of some kind of polynomial scaling overhead in the epsilon is considered doable. But you're certainly right that digital simulation because of the trotterization error could be not very ideal. They could be more demanding in terms of resource, which is why people believe that analog simulations has made more progress and potentially more realistic in the near term. Does that answer your question, Eugene?
Yes, yes, yes. Mm-hmm.
Great, thank you. Okay, so now let's be a bit more precise because we want to study this concept a little bit more rigorously. And what do we mean by simulation precisely? One possible definition is what we call the full spectrum simulation, which is recently formalized by Bravi, Hastings, and Cuban, Montadaro, and Pidock. And the idea here is that if you take the spectrum, the full set of eigenvectors and eigenvalues of the original Hamiltonian, so these are basically the states of the original quantum system, and we say that it is simulated by H tilde if they are reproduced as the lower lying part of the spectrum of H tilde below some energy cutoff delta, and in the sense that all of the eigenvectors are encoded by some operator V, which is some kind of local encoding that preserves the locality of observables. And also there will be very small errors between the eigenvalues, the energies. So more precisely, this means that the operator H tilde restricted to the eigenstates below a certain cutoff has to be sort of epsilon close to the encoded operator H. Well, this definition allows H tilde to reproduce all of the static and dynamical properties of the original system H. We know that it might be maybe a bit too strong in many contexts, because in physics, we often really only care about the low-lying part of the spectrum or the low temperature part of the spectrum and not the full spectrum. So motivated by that, Dorit and I have came up with a weaker notion of simulation, which we believe is of independent interest. Here, we only care about simulating sort of a quasi-degenerate subspace of low energy states that's separated by some spectral gap from the states above. And we actually can allow this spectral gap to, in general, to be vanishing. It doesn't have to be, constant as the system size goes to infinity. But regardless of the precise definition of the simulation we use, a very fundamental and natural questions to ask is, when can we make the simulating Hamiltonian H tilde simpler in some sense? And to the best of our knowledge, I don't think there has been any rigorous analysis of the minimum resource required for the simulation before our work. So in our work, we address this open question of simulation resource by considering the specific problem of simplifying the interaction graph of Hamiltonians, which we call sparsification. So in the classical context, there are two natural goals for sparsification of CSPs. One is degree reduction. This turns out to be always possible via a simple construction that I will describe now. So degree reduction is, if you have a complicated interaction graph, potentially you have vertices that have a high degree. So degree here just means the number of edges with a number of other nodes that that vertex is involved in. So if, for example, if you take this node in black on the left, which has a high degree, you can reduce the effective degree very easily by a very simple construction that replaces the node with a cloud of nodes that are connected by the equality constraint. So you can see that, if the original system, has some satisfying assignment, it can easily be mapped to the satisfying assignment in the new system with a new sort of extra set of nodes. But this idea is kind of hard to generalize to the quantum case, because there is something called the node cloning theorem in quantum mechanics, which tells you that you cannot really enforce an analogous version of the equality constraint. You cannot really copy unknown quantum states, unlike in the classical case, because in the classical case, if you have a 0, you can always just copy it to 0. But if you have a general quantum wave function psi, that you don't know a priori, it's almost impossible. It's basically impossible, provably, that to also copy it to another quantum system. So it's the future of degree reduction because of the node cloning theorem is unclear, but we will get to that. Another task that we're interested in is what we call dilution, and this is the goal. The goal of here is to reduce the number of edges or terms in the interaction graph. And it turns out that this is sometimes possible, as we illustrate with the example CSPs here on the complete graph. So here on the complete graph, we can imagine having sort of constraints where we forbid the appearance of two excitations. So we forbid the appearance of two ones next to each other. But we can simulate the same kind of CSP by replacing the n squared number of edges by one that only has order n edges, by adding a linear number of trilocal constraints that uses ancilla to count the number of ones. So because of the fact that in the original system in purple, the satisfying assignments are the ones that are either have 0 excitations or 1 excitations. You can use this trilocal constraint to simply count the number of excitations on the black nodes, and then you will only get a 0 energy if and only if the number of excitations here on the black nodes is less than or equal to 1. So I hope that is clear from the picture. And so now, in the context of quantum mechanics, we're interested in basically generalizing this task of sparsification to the Hamiltonian context, where we care about quantum constraints, not just classical constraints. So these are non-diagonal Hermitian matrices. And we're interested in this because you can potentially save resources in quantum computation, because if you have a complicated Hamiltonian or interaction graph that's hard to implement, and you can map it to something simple, that might make it easier for experiments to to actually realize. And also, just as a theoretical tool, if you can map complex systems to simpler ones, it might be easier to study them. And also just fundamentally from a complexity theory perspective, these ideas of sparsification is really very important in proving very basic results in classical computer science, like the PCP theorem. So if you're interested in the question of whether or not there's a quantum version of the PCP theorem, or maybe if you're interested in the question about the universality of classes of different Hamiltonians, this sort of mapping we believe is of crucial importance. Okay, so armed with the definition that I have described, and also the set of questions that I have described, we ask: is it possible to simulate a Hamiltonian H by another H tilde whose interaction graph is degree reduced or diluted? Well, it turns out that in contrast to the classical case, where degree reduction is always possible, in the quantum case, we proved that it was actually impossible in general to reduce a degree to a constant, assuming that you only have bounded interaction strength and local encoding. And so that's kind of a negative result, but we were also happy to show a complementary positive result, is that we can show that you can always reduce the degree of the interaction graph to a constant if you allow the interaction strength to grow polynomially with the system size. And lastly, on the question of dilution, we showed that there's actually a complexity barrier, a complexity theoretical barrier to this issue, in the sense that there's no way that an efficient algorithm exists to construct a diluted Hamiltonian unless something called the polynomial hierarchy collapses to the third level. So most of you would not understand what I mean, but basically it's some version of assuming that P does not equal to NP. It's something that computer scientists really believe to be not true. So if they're right, then there's no classical algorithms that can do the dilution that we want. Okay, because of the no-go nature of the result of theorem 1 and 3 here, we actually proved these results under the relaxed definition of gap simulation, as opposed to the full spectrum simulation that I mentioned earlier. And I will note that because impossibility results in a relaxed framework are of course stronger. So our results may actually appear stronger than they seem, because we only care about simulating the some kind of degenerate ground states, not the full spectrum. Okay, so I will now briefly describe how we showed our main result, which is the no-go theorem for quantum degree reduction. So here we show that it's impossible to reduce the degree to a constant with a small error, assuming that the interaction strength is bounded and the encoding is local, but we allow for any number of extra ancillas or terms. And the idea for this proving this theorem is something called the contradiction by correlation. And we make use of the fact that there is a very nice result by Matthew Hastings and Toru Komai that shows that if you have a spectrally gapped subspace of ground states in a many-body quantum system, it necessarily has some sort of decay of correlation. So if you look at the expectation value of observables located at psi I and j, they have the correlation between them must decay exponentially as a function of the distance between the support of the observable, assuming that the ground state is gapped in spectrally. So using that, we came up with a counterexample, which is shown here. So this many-body system that we constructed, Hamiltonian HB, is given by sort of this XXZ model. So you have all-to-all interaction on a complete graph where each qubit talks to every other qubit with sort of this sigma z minus sigma x minus sigma y term. And it turns out that you can show that this model has a unique ground state that has a constant spectral gap given by coherent superposition of all the bit strings where half of the bits are 1 and the other half are zeros. And this is a highly entangled state. So our proof is based on the contradiction that uses sort of a modified version of the earlier decay or correlation result that we showed in the previous slide. And specifically, we showed that under this ground state, you can show that the correlation between the observable xi and xj between every pair of qubits of particles has to be roughly on the order of 1/2. But now, if you assume that the interaction graph of the Hamiltonian that you map to has constant degree, that means that there must exist support between two different particles that you map to that has a distance on the graph that scales roughly log n, where n is the original system size. So if you kind of plug that distance back into the formula in the inequality here, you can see that this is the contradiction, because 1/2 is not less than or equal to some number that is vanishing with respect to the system size. So we have shown that because of the existence of this counterexample, it's impossible to reduce the degree to a constant under these assumptions in general. Now, for the complementary result, where we show that the degree reduction is possible if we allow for a large interaction graph, it can be sort of shown as follows. So previous constructions to do degree reduction uses something called the perturbative gadgets. And in general, they require exponential interaction strength. So need the interaction between particles to grow exponentially with the original target system size. But with our construction, we were able to show that you can do this with only polynomial number of interaction strength. And this is shown via the following idea. So if you take input Hamiltonian, where I have written here as a decomposition into eigenstates, but you don't need to know them explicitly. And we can consider mapping them to something called the quantum phase estimation circuit. So this circuit, what this circuit does is that it takes any eigenstate of the input Hamiltonian H as input, and it writes down the energy eigenvalue as a bit string on the ancilla. And once you have a circuit, it's much easier to do degree reduction compared to if you only have a Hamiltonian, because what you can do is that you can take a circuit like this, and in the context of circuit, degree just means that how many times a particle is acted on by gates. You can then take the circuit and add a bunch of ancilla qubits and swap gates that swap the state of the quantum state of each particle after each gate to some fresh ancilla that are essentially copies of the original qubits, and then you perform the subsequent computation in the circuit on the new fresh ancillas, and the original qubit is never touched again. So through here, you can see that degree reduction is easily possible, and you can make this construction sophisticated enough so that you can make the circuit two-dimensional in a spatially sparse way. Then you can take this 2D spatially sparse circuit and map it to a 2D spin lattice model, for example, using something called the Kitaev circuit to Hamiltonian construction. And the basic idea here is that you can write down a Hamiltonian whose ground states encode the computational history states of the circuit. And we know that this construction works even if you restrict the final simulator Hamiltonian H-Shoda to, as I mentioned, 2D spin lattice models, as well as a 1D chain of spin 4 particles. So I will summarize what I have said so far and just as a sort of a short break before I move on to the next part, which I will go more quickly. That what I have shown so far is that unlike classical computer science context, generic quantum degree reduction is actually impossible unless the interaction strength diverges. And we also showed that in contrast to the exponential scaling of interaction strengths shown previously in the earlier constructions, we came up with a new construction that only uses polynomial interaction strengths, which is much more efficient. So now I will move on to the second part, which is about quantum optimization. And the idea here is that instead of simulating constraint satisfaction problems, we also want to optimize them. And we have so in this context we have some cost function, which is the number of constraints that you say you want to satisfy, which is defined on m bits, which in here I allow them to be either plus or minus 1. We want to find an assignment z star so that the cost function is maximized. So for example, a very a famous example of the optimization problem on CSP is the max cut problem. So here is the problem is if you are given a graph, you want to find a bipartition of vertices so that the maximum weight of edges between the two set of vertices is maximized. And the cost function here can be written as a sum of terms over the edges, where each term here correspond to 0 if the edges have bits that disagree, that agree, and if they disagree, then this term contributes 1. And another problem that we're interested in is the maximum independent set problem. So here, again, it's a graph problem. And when we're interested in finding independent sets, which are basically any set of vertices where no edge exists between any pairs of vertices in the set. And the maximum independent set is simply the largest such independent set, and you want to find them. And again, the cost function here can be written as a sum of terms that are only acting locally on the graph. You have a sum over the different node vertices that counts the number of ones or plus ones. So I've converted the variable z's to n here, and you also penalize the appearance of 2 ones next to each other on every edge with some penalty v that's much larger than 1. So both of these problems are very simple to understand, and they also have many applications in across all fields. And in general, we actually don't necessarily care about restricting to these problems. And we're interested in basically solving these problems with the quantum algorithms. That's also somewhat general purpose, and that is the algorithm of quantum approximate optimization algorithm, which is shortened to be QAOA. So the idea here is that if you start with a bunch of qubits that correspond to the vertices on the graph problem that you want to optimize, you initialize them in something called the plus state. And then the idea behind this algorithm is that you can apply 2 unitaries. One is e to the I gamma c, which is evolution under the cost function. You can convert that to a Hamiltonian in this case. The other one is e to the I beta b, where b is the sum of the single qubit x terms. So this corresponds to single qubit rotation. And you want to repeat this, say, p times. And then you perform a measurement on the output wave functions, and you get some bit strings z1 through zn. And then the idea is to do this many times and compute the average. And you also try to feed the average that you compute to a classical computer in a closed loop so that you can find the parameters gamma and beta to maximize the cost function value obtained. So this is the idea that uses the quantum resource that you have along with the classical resource, so that you can try to solve this optimization problem to the best of your ability. And this algorithm is attractive for a few reasons. It's simple to understand and easy to implement, and it also has a nice property that it monotonically improves with the depth p, and it also is guaranteed to get to the global maximum solution as p goes to infinity. But we also have a lot of open questions about this algorithm because we don't really know how to best find the optimal parameters, gamma and beta. And it is also a very open question, how well does the QAOA, this algorithm do on all of these optimization problems for given P. So I will describe a bit about the previous results that we know about the QAOA. So the previous result that before our work is have been done to analyze the performance of the QAOA via something called the subgraph method. So the idea here is that if you take your cost function for max cut on 3 regular graph, for example, and you look at p equals 1, and if you want to look at the expectation value of this cost function, it consists of basically a sum of terms that looks like this. You have the cost function edge in the middle, and it's sort of sandwiched by the quantum state, which is given by sort of this e to the I beta, e to the I gamma c acting on the initial state. So if you look at the Heisenberg picture operator in the middle is supported on sort of 3 types of subgraphs when you have a 3 regular graph. For example, if you look at a term that corresponds to the edge between node 3 and 4, it corresponds to subgraph type 2. And if you have a term that corresponds to the edge between node 8 and 14, it corresponds to subgraph type 3. So what you can do is that you can take any graph, no matter how large it is, and just count the number of subgraphs that you see. And you can get a worst case guarantee that the QAOA can get a cost function value at least 0.69 times the maximum at p equals 1. So this is very nice because it gives you a provable guarantee of the performance of the quantum algorithm analytically, but it's really difficult to analyze this algorithm for higher P because the complexity of simulating this this expectation value classically on a classical computer scales doubly exponentially in P.
Question, Leo?
Yeah.
So just to understand this algorithm a little better, you always pick the gates to be the cost function and single qubit operations, is that right? You had a choice for creating this variational state?
In this particular context, yes, but there are versions of the QAOA that I would discuss briefly. That is a variant of that. You can also consider slightly different driver other than just a single qubit rotation. You can consider constraint rotation, which is more natural in some experiment, for example. But yeah, I mean, this is sort of just a starting point as a framework to try to understand this type of algorithm, but certainly you can consider more general form.
But what are the considerations? You're trying to pick something which is kind of easy to implement, or could I take
it depends on who you ask. I think that for experimentalists, yes, you want something that's easy to implement. But for theorists who are interested in provable, algorithm performance guarantees, you also want something that's easy to analyze. Which is why it's easier to stick to sort of local single qubit rotations and cost function evolution because they have a clean way to analyze this. For example, using the subgraph method. But certainly it's a balancing act, between whether or not it's easy to implement versus easy to understand.
Right. And with this choice, you're saying you can prove this bound, for example, at least for one layer of this of application with just the single qubit and the cost function. That's the result over here.
Yes. Indeed, and that is really what kind of drew a lot of excitement in this field, because previously there hasn't really been a lot of provable results for optimization using quantum computers, and I think briefly, I think for like almost a year, I think the QAOA at depth 1 was beating the best known classical algorithm for a particular problem until later on the classical computer scientist guys got together and figured out a way to match the performance.
So there are classical algorithms that can also give you some guarantee for this cost function, like a bound like this?
Yes, there are. And I think then it is now an open question, what happens if you go to higher depth? Because, ultimately classical and quantum algorithms do perform very differently, especially at the depth where, for example, the algorithms becomes more non-local. Here is sort of local because you only are confined to just sort of subgraphs.
Right. Okay, thank you.
Great, thank you for the question. Yeah, that was, I think, yeah, that's hopefully illuminating. So this analysis via subgraphs also shed light into some properties of the algorithm, and this is something called landscape independence. And this is sort of the idea that if you take the expectation value, the cost function for a given graph, of course, this depends on the graph because the cost function depends on the graph, the wave function depends on the graph. But what's remarkable is that if you take the system size n go to infinity, you can actually show that this graph dependent cost function converges to a graph independent value up to sort of 1 over square root of n fluctuation. And this is sort of because of the fact that if you have a large enough random graph, all the different kinds of subgraphs that you see sort of converges to some kind of fixed fraction. And what this really means visually is that if you look at two different graphs and you look at the landscape of the cost function, they look almost essentially the same. And that also, is very helpful because, if the cost function landscape looks the same, the optimal parameters for QAOA will also be very similar. So this is, very helpful for experimental implementation because you can, if you work hard to find the optimal parameters for one, you can then, apply it to other problems, similar problems. And another thing that also came out of this is that, you can also show limitations of the QAOA. And because of the fact that at very low depth, you only see subgraphs, you don't see the low graph, you don't see the whole graph, there is necessarily a limitation to how well the QAOA can do. And for example, if you have a deregular graph, the subgraph that you mostly see just by probability theory is mostly trees whenever the depth is sort of much less than log n. And because of the fact that, in the ensemble of regular graphs, there are bipartite ones where all the edges can be cut. And there's also typical ones where a lot of the edges cannot be cut. And when you don't see the whole graph, they all look the same to the algorithm. So there's no way to really, perform well on the bipartite graphs when, you can only satisfy a number of edges that's just as many as you can on a typical graph. Yeah, I mean, so you really, what this is showing is that, in order to have, a good performance on this algorithm, you really need to go to a regime where P is large enough that the algorithm sees the whole graph. And to go to a higher P, we need to sort of be able to do this optimization more efficiently. And one of the things that we discovered is that there's actually a pattern in the optimal parameters of QAOA. So if we look at, for example, max cut on three regular graphs, and what we did is that we took some graphs that we randomly generate with 18 nodes, and we went to P equals 5, and we just did like a brief brute force search for the optimal parameters gamma and beta. And what we discovered is that after fixing some gauge to reduce the redundancy in the parameter space caused by some symmetries, there seems to be a very smooth parameter path that emerges for the optimal parameters. And this is true not only just for one graph, but also for 10 graphs. For example, I'm plotting the optimal parameters for 10 different graphs simultaneously on this plot. And more dramatically, this is the parameters for 100 graphs. So we see that there is indeed a clustering of parameters from different graph instances as predicted by the landscape independence. And also that, not only that they cluster, they do exhibit this sort of smooth parameter path pattern. And as we sort of vary the depth P, we see that, these optimal parameters, not only are they smooth, but they also sort of look like smooth deformations of each other as you increase the depth. So for example, I'm showing here the optimal parameters for 100 graphs simultaneously. And we see that the parameters are sort of, of similar range, and it's almost seems like there's a smooth underlying curve that governs the parameters. And this is true not only for three regular unweighted graphs, but also a bunch of other graphs that we have tried. So this has inspired a heuristic strategy to efficiently find optimal parameters by simply taking the optimal parameters at a lower depth, say P equals 3, and sort of interpolate it and then stretch it to kind of generate a good initial guess for the optimal parameters at P equals 4, and use that as a starting point to find a good local optimal solution. And it turns out that this strategy is actually very powerful because if you, for example, look at this plot for on the top right for a particular graph that we have tried, we can compare the heuristic algorithm for finding the optimal parameters to the brute force sort of random initialized kind of runs. By that, I mean just basically you start with 1,000 different random guesses for the gammas and betas and just sort of try to, find a local optimum and then keep the best one. So you do see that at low depth P, they agree with the best, the heuristic agrees with the best found by the brute force. And at higher depth P, the brute force is no longer enough to find the solution, the best solution, but the heuristics continue to improve. And we have also characterized the number of sort of this standard strategy of random initialization that's needed to match the performance of a heuristic. And we do see on this log linear plot that the number of such runs necessary does scale exponentially compared to our heuristic. And one more thing that we sort of discovered is that there's actually an interesting mechanism that came out of QAOA that can be sort of understood via a comparison to quantum annealing. So quantum annealing is another algorithm that sort of takes the cost function and also the single qubit rotation and sort of evolve with them in a smooth way. And this is also known as the adiabatic algorithm. And as we can see that for a particular graph that is considered hard here, because the runtime for the algorithm is like very large. So I'm plotting the population of the ground state, which is the solution, as well as the first excited, second excited, third excited states. And we want to maximize the population of the blue, which is the ground state. And in order to get to a good population, you see that you need time on the order of 10 to the 6. And this is agrees with the prediction from the adiabatic theorem, which tells you that the time needed roughly scales as 1 over the minimum spectral gap square. And in this particular instance, that is 10 to the minus 3. So 1 over that square, does give you the adiabatic time scale of 10 to the 6 for this instance. Now for QAOA on this graph, we show that you can actually achieve a huge population in the ground state with a runtime that's on the order of like 40. And here, notice that the x-axis is very different. On the left is a log scale. On the right is a linear scale. So you can see that we do have multiple orders of magnitude improvement in the computation time necessary to prepare the ground state if you have QAOA versus just a generic adiabatic quantum annealing. So the basic idea behind why the QAOA is able to do this is that it turns out you can exploit something called shortcuts to adiabaticity. And this is so what we call a non-adiabatic mechanism of QAOA. So the idea is that for standard instances where you have a very small gap, the adiabatic algorithm follows sort of this trajectory in green, where because of the fact that it's not slow enough, it will unfortunately necessarily goes to the excited state. But what the QAOA does appear, as it turns out, is that it's able to sort of couple the ground state and the excited state before the small gap, and accumulate population sort of in the first excited state as shown on the right before this crossing, and then use the crossing to come back down to the ground state. So it turns out that in some regimes, the QAOA can be potentially understood as a systematic approach to find a better non-adiabatic path to solve the optimization problem. And for the last part of my talk, I would just go over the analytical result that we have on understanding the performance of QAOA on the Sherrington-Kirkpatrick model. And this is the problem of minimize or maximizing the energy of n spins that are coupled in an all-to-all way with random sign couplings. And because of the fact that this problem is defined on a complete graph, it has unbounded vertex degree, which means that we see the whole graph even at finite depth. So we don't have the same limitation that we discussed earlier about low depth, where you don't see the whole graph. And there's a potential for quantum algorithms to do well in this situation, even at constant depth. Now, in the worst case, this problem is NP hard to approximate, even with a approximation ratio factor that decreases with system size. But for the typical case, or the average case, is actually known what the maximum energy of typical instances, and this is a famous result by Giorgio Parisi in the 1970s, who predicted that the maximum energy almost surely for every instance that you can generate for this model roughly approaches as 0.763 times n as n goes to infinity. So this result is very nice because it tells us what the maximum energy is, but it doesn't actually tell us how to construct the solution. So what do we know about the complexity of actually solving this a given typical SK problem and find a solution? Well, we believe that the simulated annealing algorithm, which many of you probably know, is believed to actually fail for this problem in the sense that you will sort of encounter a threshold just below the maximum energy that you cannot anneal beyond. And another very powerful classical algorithm is called semi-definite programming, and that you can get a proportion of you can get an energy that's roughly a T over pi, which is 0.636, and that is pretty good, but it's not quite the maximum energy. And recently, assuming that a conjecture that the SK model does not have something called the overlap gap property, a computer scientist, Andrea Montanari in Stanford, was able to come up with the algorithm that's able to output a solution that's epsilon close to the maximum energy in time that's only polynomial in the system size and also the precision parameter epsilon. So assuming this conjecture is true, there is not that much improvement on these classical algorithms. But because this model is so well studied, we still want to ask, how does the QAOA do on this problem? And can it potentially match the performance of Montanari's algorithm? So I would just tell you our result. We were able to actually come up with a way to evaluate the performance of the QAOA on the SK model for very high P with a method that only scales 16 to the P where P is the depth. So even though you can see that this is sort of an exponential scaling in P, but this is much better than 2 to the 2 to the P, sort of this doubly exponential time that was required by the previous method of subgraph analysis. And here are some results. So at P equals 1, we show that we can get to an energy that's 0.303, and as P increases, we steadily improve. And in particular, at P equals 11, we're able to show that there exist parameters of the QAOA that beats the value achieved by this very powerful classical algorithm known as semi-definite programming. So if you remember, semi-definite programming achieves T over pi, which is roughly 0.636. So just barely in the third decimal, QAOA performs better at P equals 11, but it still continues to improve as we go to higher P. Another result that we're able to show is that there is actually something called concentration of QAOA on this model. So what that means is that we're able to show that this variance, the expected value of the cost function square is the square of the expected value in the infinite size limit. So that's sort of abstract, but I'll tell you what it really means. So it actually means two things. The first thing is that there's a concentration over instances. So that's basically the landscape independence property that I discussed before. And what this means is that for two different instances, the cost function expectation value as a function of the parameters of QAOA almost looks the same between any two typical instances. But there's also an additional concentration property, which is what we call concentration over measurements. And this is basically that if you actually measure your quantum wave function given by the QAOA in the computational basis, the value that you achieve concentrates at the expectation value itself. So that basically means that the variance of the energy that you get in the quantum wave function is also very small. So what this what this means is that with probability tending to 1 as n goes to infinity, if you run the QAOA and measure in the computational basis, you will give you a bit string which has a cost function value that's close to the quantum expectation value, which is itself close to the infinite size graph independent value as n goes to infinity. So just in the last few slides that I have left, I will just tell you briefly about some ideas that we have come up with that we're actively using to implement these algorithms in the experiment. So now I will sort of switch gear from talking about max cut and SK model to something called the maximum independent set that I discussed before. So instead of doing the standard QAOA, we considered a variant, which is alluded to by Ashwin just now. That instead of just evolving with the cost function and single qubit rotation, we consider constraining our quantum state to just the states that correspond to independent sets. And that basically means that the cost function just counts the number of ones on the graphs, and the rotation, the driver operator B is sum of sigma x's, but now the sigma x are kind of conditional on basically remaining in the space of independent set states. So because of that, we start our quantum wave function in the state of all zeros. So that means the empty independent set. So it is a valid independent set. And then we applied this operator B and C alternately in the hope that we can find some parameters beta and gamma, so that the cost function value, the number of ones, is maximized. So the reason why we care about this particular formulation is that in neutral atoms, there's something called the Rydberg blockade that naturally enforces this constraint of staying in the independent set. So if you kind of consider encoding your qubits in sort of this atomic state of zeros and ones, where one is a Rydberg state, and this Rydberg state one sort of has this very strong interaction that we call the Rydberg interaction that decays as sort of 1 over r to the 6 here, and that basically means that below some distance cutoff, the interaction is huge, but outside of that distance, the interaction is small because it's 1 over the distance to the 6th power decays very quickly. So that basically means that within some within this blockade radius that we call RB, you're really not allowed to excite two Rydberg states that are near each other because of the fact that the interaction shifts them out of the resonance of the laser. And what this means is that we can efficiently encode the maximum independent set problem on the so-called unit disk graph very efficiently under this blockade approximation. And this was a key insight that we identified in joint work with Hannes Spiegler, Chantal Wang, and so on, and Misha in our group. So because of this very hardware efficient way of encoding the problem, we have decided to start pitching this to the experimentalists in our group, and happily they accepted our proposals and have started to actually realize this algorithm in the experiment. So I just kind of briefly show some results, but for those of you who are sticking around for the defense later by Alex Kiesling, you will hear more about this. So the idea is that you take a unit disk graph like the one shown on the left, and the idea you want to find the maximum independent set. For example, the nodes that are labeled in red here, and if you want to solve this problem, a very natural way to do this with a neutral atom is to simply use the rearranging capabilities that they have developed with optical tweezers and move the atoms to the location of the vertices and put them close enough together so that their blockade radius correspond to this edges that are drawn between any unit disk in the graph. And by then simply shining your laser with the right Rabi frequency in the right post shape profile, you can then map this to the quantum QAOA algorithm on this graph, and then by detecting how many atoms are in the Rydberg state at the end of the protocol, you can identify nodes that are believed to be a good independent set. And here's some preliminary data that the experiments have shown. And for this particular graph, the maximum independent set has 57 nodes. And as you can see that, despite the fact that we have a very big, system size of 100 and almost 180, we're able to get basically 14 out of 5,000 times observing the largest independent set. So that's roughly just shy of 1%. So this is sort of, that may not sound like a lot, but this is actually very significant because if you consider the entire possible space of states that you can have when you have 180 atoms, that's like, exponential in 180. And to be able to achieve such a, significant population in the maximum independent set is quite impressive. And we have also started to, optimize the parameters of these algorithms by, probing the parameter space of the QAOA.
Question?
Yeah.
So you explained this maximum independent set as a hard problem.
Yeah.
In general, but it seems like here you have like a geometric embedding of that problem. Like the things that are connected are nearby in some sense, right?
Yes.
Does this simplify the problem?
To some extent, yes. So it is still true that this restricting to this sort of low geometry in 2D, that the graphs are still NP hard in the worst case, so they are considered hard to solve in the worst case. But they're unlike the sort of the more general graph case. For this unit disk graph, there is something called a polynomial time approximation scheme that can sort of run. You can run a classical algorithm in time that's only polynomial in the system size, but find an epsilon approximation solution in time that's polynomial in system size but exponential in epsilon. Whereas for general graphs you cannot do that. So it does make it a little bit simpler, but still it is very hard if you want to get a good approximation ratio if you want to get a small epsilon. I
see. So did you benchmark it against the classical algorithm, this particular instance?
Yes. So for this particular instance, we were able to actually solve it. That's why we know that the independent set size is 57. But we do see that for state of the art exact algorithms, for example, solving these graphs on average takes exponential time. But there are heuristics algorithms that perform better, especially if you consider not necessarily caring about the exact maximum independent set, but also the approximate solutions. Yeah.
I see, but I don't know what the appropriate comparison is, but could you make a comparison against the best classical algorithm for this particular problem, which has similar characteristics? Like, I guess this is also doesn't guarantee a solution, right? So
yeah, so that is actually active project that we're working on, and I didn't include this in these talks because, as you can see, I'm already running quite over time. But yes, we are comparing it to, for example, analogous algorithm like simulated annealing, and there we see that, for example, maybe on average, the simulated annealing has a scaling that's a power law in this epsilon parameter. But potentially, we can observe a better scaling in the exponent, for example, in the quantum algorithm, or perhaps the quantum algorithm can even have a logarithmic scaling. We don't know. So that is certainly something that we are currently actively trying to understand.
But maybe I'm asking not so much about the asymptotics of the scaling, but just literally how long it takes.
Oh, I see. Okay, so I think that if you want to find the exact solution, I think that if you want to go beyond, say, 400 or 500 nodes, I think that it would take, a day. And I think that for simulated annealing, for more other, more like kind of, heuristic, but like, perhaps like more tailored algorithms, you can maybe find the solution for like 500 nodes in like, a minute.
I see. Okay, thanks. That's helpful.
Great. So I will now conclude my talk by just kind of summarizing my contribution. So on the problem of analog quantum simulation, we were able to prove lower bounds on the resource required for the task of Hamiltonian sparsification. And we showed that, specifically for the task of degree reduction, there is a fundamental difference between the quantum world and the classical world. And we also came up with exponentially better construction for general simulations compared to previous proposals. And as outlook, we want to also, understand, what we have shown are worst case results. So we have shown that there are, examples that we construct that's really hard to, reduce the degree, for example. But perhaps like on average, many more Hamiltonians are sparsifiable than previously thought. And we want to, understand the landscape of when Hamiltonians are sparsifiable. And in addition, even though we have came up with better constructions for general Hamiltonian simulations, we want to, improve the constructions so that they're, becoming more experimentally relevant regime, and that's more ready for implementation in the lab. And on the question of quantum optimization, we came up with an efficient heuristic method to optimize QAOA parameters using ideas like landscape independence. We have illustrated that there is a non-adiabatic mechanism that one can utilize in the QAOA. And we also have provided rigorous analytical results for the QAOA at very high depth, specifically for the SK's thin glass problem. And we show that it can be some classical algorithms and potentially match the best one. And some open questions in this context are, we still want to understand the asymptotic scaling of the QAOA, for example, for the SK model, beyond, just p equals 12, we want to see like what does it converge to as p goes to infinity, and we also want to understand, the QAOA on other versions of the SK model where classical algorithms might fail because, as opposed to the SK model, where there is no overlap gap property, that's this OGP. If you take the three-body coupling version or the four-body coupling of the SK model, it is known that they have this property called OGP, where necessarily, classical algorithms, many of them will fail. And finally, we are in a very exciting time where we can test these quantum algorithms. That's really hard to analyze by actually implementing them in experiments. So I'm really excited to find out what we can actually learn from observations and potentially give us more insights about how these algorithms could work and potentially developing better algorithms that will be useful for humanity. And that's all I have. I'm happy to take any more questions.
All right, thank you, Leo. So, any questions from committee or anyone else in the audience? So I actually have a few. I think I learned something new from the thesis defense, which is quite remarkable. But so, okay, I'll just ask one, so for this part, for your work on this kind of sparsification and so on, I mean, all of these kind of mathematical proofs have their limitations. And I mean, for example, like even, in your own work, the stuff that you guys are now discussing with, Hannes about, for example, reducing the kind of non-unit disk graphs to unit disk graphs. Does that sort of violate your own proof?
No, actually, it's actually a very good example of why, degree reduction is easy to do in the classical context. So the thing that Hannes, that Misha is referring to is that we're working with Hannes to reduce the complicated MIS problem, which is a classical problem on potentially complicated graph, to a graph that you can embed in 2D. But because of the fact that these are classical problems, it is already known that there's in general ways to do the degree reduction. And what we have shown here is that if you kind of take that idea and generalize it to the quantum context, there's a fundamental limitation because of the existence of quantum entanglement and strong correlations of certain gap ground states.
All right, so last call for physics questions.
Yeah, hi, hello. Could I ask a question with maybe very naive. So you mentioned like that finding the quantum ground states is maybe quantum easy to be verified, but quantum hard to solve. Could you give more comments on that? Because naively, I will think, okay, if you have a quantum analog quantum computer, like something with optical lattice, for example, ideally, if you can go to lower enough temperature, you naturally go to the ground state. So is that like already a solution, finding the solution of the ground state of the quantum Hamiltonian, or it is not?
That's a very good perspective. Thank you, Wenchao, for the question. So you know, what you have described is essentially that, you know, yes, for a lot of systems, you can indeed cool the system to below, you know, some arbitrarily low temperature and find the ground state. But there are, you know, other problems, other system like spin glass or you know, quantum spin glass that is, you know, believed to take exponential time to relax to the ground, to low temperature. So I think that, you know, that perhaps provide an intuition when you have sort of disordered systems. In general, you know, it's hard to actually cool them below some critical temperature.
I see. Then I have a follow-up question. So how you actually verify it is the ground state? How you know it's actually no other states is lower than that energy? Could you
Okay, so basically what you can do is that you can so verification here means that, you know, it's verifying that, you know, there exists a quantum state that has an energy below some threshold. And you can easily verify if that statement is true by, you know, having someone provide you with a quantum state. And then you can simply run the quantum phase estimation algorithm on that state, and then basically extract the energy relative to the Hamiltonian. Or you can actually, I guess, also just essentially measure the energy directly. So that's how one will actually verify that, you know, if you give me an actual quantum ground state that satisfies this, you know, inequality that is below some energy threshold, then I can verify by just, you know, like studying it with my quantum computer.
Thank you.